Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we started a discussion on the LSD, that is Latin square design. And in that lecture we had understood the basic concepts, definitions and fundamentals behind the Latin square design. We had understood that why it is called a Latin square design, what is a Latin square and what are the various types of Latin squares depending on their properties and what are their properties. And those properties are going to be used when you are trying to consider different types of Latin square design, which are essentially the different variants and based on the concept of Latin square designs. Right. So, now in this lecture I am going to talk about two topics. The first part is that now you have learned how in the setup of a Latin square design. Now, how to conduct the analysis of variance, that is the main issue. So, in this lecture first of all I will be discussing about the analysis of variance in the Latin square design, and after that I will take up one more topic which is about missing plot technique. So, what is this? You know that whenever we are trying to conduct an experiment in a real field, means a real life experiment, then it is possible that sometimes some data may get missed. For example, if there is a clinical trial in which the patients have been asked that they will come every week, they will be given a dose of medicine, and after that some recordings have to be done. And this process has to be continued say for 5 weeks. So, every patient has to come every week 5 times. Now, there is one patient suppose who comes first week, second week, but third week the patient does not come, and then the patient comes on fourth and fifth week. So, now in this case the data in the third week is now missing. Similarly, in case if somebody is trying to conduct an experiment in the field with the crops, and suppose the field has been divided into different plots, and say somehow the crop in the one field gets destroyed because of any reason. Now, what will happen? We will have all the sample observation, but the observation from a particular plot is getting missed. So, now there can be various such situations in which the data can be missing. There can be situation where only one data is missing, or there can also be situation where more than one data is missing. So, the question is how to handle it. Well, in statistics there is a whole area which is called as missing data models, which takes care of such aspect that how to handle the situation in this case and how to draw the statistical inferences from the remaining data. So, one simple option is that instead of you try to conduct the experiment once again, that will result in a huge cost and loss. A better option is that whatever data we have, based on that data we try to estimate the missing data. So, we are simply trying to find out the value of the missing data on the basis of the data that we have observed, and after obtaining this value or after estimating this value, we will substitute this data in the place of missing data. Now, the sample will look like as if we have all the data points, and based on that we can conduct the statistical analysis. So, this is basically called as imputation. So, this imputation technique is quite popular in the missing data models. So, now in this lecture we are going to understand how to handle this missing data issue in say in the type of design what we have considered up to now. For example, we have considered here CRD, RBD, LSD up to now. So, I will try to take an example from RBD as well as LSD, and I will try to show you that how you can estimate the missing value, and after that what are the changes which are going to occur in the analysis of variance, so that our statistical conclusions are valid and reliable. So, let us begin our lecture, and first I would try to address here the issue of analysis of variance in case of Latin square design. So, let us begin our lecture. So, now just for your remembrance, in the last lecture we had defined a Latin square of order P as an arrangement of P square symbols in cells, and these P square symbols are arranged in P rows and P columns such that each symbol occurs once and only once in each row and in each column. And we had considered an example where we had written Latin square of order 4, where we had considered or we have chosen 4 symbols A, B, C, D, which are the capital letters, say capital A, capital B, capital C and capital D, which are actually our Latin letters. And then these 4 alphabets are written in such that these letters occur in every row and every column once and only once. Right. So, you can see here we have here A, B, C, D, B, C, D, A. So, C, D, A, B and D, A, B, C. So, no symbol occurs more than once in any row and in any column. And based on that we had considered different types of properties of the Latin square. Now, we come to the analysis. So, we assume that you have chosen Latin square design, and based on that now you know how you are going to conduct the experiment, and based on that how you are going to conduct the data collection process, right. Means how you are going to assign different treatments to different experimental units, and based on that you will collect the required data. So, now the question is this, when you are trying to use a particular type of Latin square which is going to control your the choice of treatment combination on which the data has to be collected. So, we have to keep in mind the principles of design, randomization, replication and local control. So, when we try to choose the Latin square, we also would like to implement these 3 principles so that we get some reliable data. So, now the first question comes here that how are we going to use the principle of randomization in a Latin square. So, we are going to consider here the case where we have only one observation in a cell. So, now you know that in case if you try to suppose select this Latin square. Now, this Latin square is actually fixed, and you have to just follow the rules which you know beforehand. So, now practically there is no randomization, and you know that where you have to give this treatment combination in the first cell, then in the second cell and so on. So, there is no randomization here. So, what we try to do here, that in order to implement the principle of randomization, we try to randomize the rows and columns of the chosen Latin square, right. So, in case if we are trying to consider a Latin square design of order P, in which we are going to consider a Latin square of order P. So, what we try to do? We just try to choose one Latin square at random from the set of all possible Latin squares of order P, right. Now, you had seen in the last lecture that given a Latin square, you can always create more than one Latin square. So, you can choose any one of them. And in some books the tables of Latin squares are also given, because when you are trying to consider some higher order Latin square, it is little bit difficult to construct the Latin square yourself. So, for the sake of convenience, those Latin squares are given. So, so depending on your choice of the order, you are going to choose a Latin square, right. And you are going to choose this standard Latin square from the set of all standard Latin square with equal probability, right. You have seen that once you can create more than one standard Latin square. So, you are trying to choose just any one of them such that the probability of selection of any Latin square remains the same. Now, you have fixed your Latin square, but now in this case there is no randomization. You are nowhere employing the principle of randomization, so that you can allocate different treatments to different experimental units. So, in order to achieve this, what we do, we try to randomize all the rows and columns. Now, the question is how to get it done. So, one simple option is that, for example, we can choose a random number, say smaller than p, say n1. And now what we try to do here, then now the second row becomes the nth row, right? And then I try to choose another random number less than p, say n2, and then suppose the third row becomes the n2th row, and so on. We can continue this process as long as we are not satisfied that this Latin square is now completely randomized. And the same process we can also do for the columns also. So, now let me try to take here one simple example, and then I try to show you that what do I mean by this statement, that you try to choose a number from the random number table less than equal to p and try to interchange the rows and column. So, for example, I take here an example of Latin square of order 5 by 5. So, what we try to do here, that we will try to randomize the rows and then we will try to randomize the column. Well, there is no reason that why I am saying that you have to randomize the rows first. If you wish, you can also randomize the columns first, because anyway this is randomization. So, the randomization means that you should not know what is going to be the outcome unless and until the experiment is completed, right. And so, whenever we are trying to consider the Latin squares of order smaller than 5, then you know you can handle them easily. So, in this case we first fix the first row and then we try to randomize the rows and then the columns. And in case if you are trying to consider the Latin squares of order more than 5, then need not to fix even the first row, just randomize all rows and columns. And if you try to understand what is the basic philosophy. The basic philosophy is that you simply want to interchange rows and columns in such a way so that you do not know which Latin square are you going to get, based on which you are going to conduct the experiment. And surely the Latin square what you are going to get, that is going to be one among those out of the total possible choice. Right. So, now let me take this example. Suppose I consider here 5 by 5 Latin square. So, there are 5 symbols A, B, C, D, E, and you can see here these are given here, like this is my first row, this is my second row, this is third row, fourth row and fifth row, which I am trying to indicate here as say R1, R2, R3, R4 and R5. And similarly, the columns can be indicated by C1, C2, C3, C4, C5. Now, because for the sake of example, suppose now I choose a random number from the random number table, and based on that I try to say now the third row become the fifth row. So, what will happen here? Now, this third row will now become the fifth row. So, you can see here this is here the third row, and now I try to rearrange and I try to bring it at the fifth level. So, you can see here this is here the same thing, right. And similarly, you can say, for example, the fifth row become the third row. So, what we try to do here, that in order to achieve this, that the fifth row become the third row, what I try to do here, I try to choose here this fifth row and I put it here at the third row. You can see here. So, now you can see that this Latin square is going to be different from the first one. And similarly, you can repeat this process again and again. My idea here is simply to give you an idea that how are you going to change it. Now, I can do a similar operation on the columns also. So, for example, I try to choose a random number from the random number table, and based on which we conclude that the fifth column become the first column and first column become the fourth column and fourth column become the fifth column. So, now if you try to just do these many operation on this one, on this Latin square, you will get here this Latin square. That is a pretty simple thing. You have to just do some exercise, try to play it just like a small game in which you are trying to interchange the alphabets. Right. So, now you can see here at this moment you have now, before you did all this operation, you had absolutely no idea what Latin square you are going to get, but now you are getting here a Latin square in which you didn't knew that which alphabet is going to be at what place, what address. So, now you can use this Latin square for the assignment of treatments, and we can obtain the observations on it without any problem. So, that you can see this is pretty simple. And My idea is that we are essentially just trying to get a Latin square where we don't know that what Latin square we are going to get, so that the probability of collection of any Latin square out of the total possible Latin square remains the same, and then all the treatments are going to be assigned according to the choice of the Latin square. So, that will also remain unknown to us as long as we are not getting the Latin square in our hand. Okay, now based on this Latin square, you conduct the experiment and you collect the data. So, now you see you are going to have here one observations in each cell. So, there are 3 factors. So, the observations are going to be indicated by 3 subscripts. So, the observations are indicated by here y with the subscript I j k. So, this is going to indicate an observation on k treatment in the ith row and gth block, and suppose they are v treatments. So, we know that in this case the number of rows, columns and treatment, they are going to be the same, because they are based on a Latin square, right. So, I j k all will have the same range here starting from 1 to up to v, right. And you can see here, if you try to have a complete experiment, means complete replication, then you will need here v into v, which is equal to v cube number of observations. But you are going to choose only v square values out of those v cube possible values, because the choice of Latin square is helping you in choosing v square values out of the v cube values. So, this triplet I j k, which I have written here in this y I j k, take only the v square values which are indicated by the chosen particular Latin squares collected for the experiment. Now, we are just going to assume the same assumption, same rules, same philosophy, same methodology that we have done in the case of analysis of variance. So, we are simply assuming that y I j k's are independently distributed as normal, and now you know this model can be written in terms of the general mean effect and the 3 factors. So, we can write it here as a normal with mean mu plus alpha I plus beta j plus tau k and variance sigma square. Now, you understand that why and how I am writing all these things without any problem. These are very simple thing, and now you see this is the advantage of doing the analysis of variance first. Now, you understand each and everything. So, now the same thing we can also express in the form of a linear model as say y I j k is equal to mu plus alpha I plus beta j plus tau k plus epsilon I j k, where I j k they are going from 1 to v, and this epsilon I j k they are the random errors which are IID, identically and independently distributed following normal distribution with mean 0 and variance sigma square. And we know that we are going to put here the constraints on the parameter like a summation over I alpha I is equal to 0, summation over j beta j is equal to 0, and summation over k beta k equal to 0. So, here this alpha I beta j and tau k, they are going to indicate the 3 effects that we are going to consider in the Latin square design. For example, earlier you had considered the 3 factors which are say driver, petrol and the car, right. So, this alpha I is going to indicate the main effect due to rows, beta j is going to indicate the main effect due to column, and tau k is going to affect the main effect due to treatments, right. So, based on that now you can conduct your analysis of variance, and you can see here that I am writing here the words like due to rows, columns and treatments, well, because there are 3 factors. So, and these observations are arranged in the rows and columns of the Latin square. So, that is indicating the effect, right. So, different books may have different names, but you do not need to worry for that, you have to just understand what are these things. Now, you have obtained the data. Now, you would like to test the null hypothesis. So, since there are 3 effects, so there are going to be 3 H naughts. So, one H naught is about the row, which is indicated by here H naught r, which is alpha 1 equal to alpha 2 equal to alpha v equal to 0, and second H naught is about the effect in the column. So, I am indicating by here H naught c, which is beta 1 equal to beta 2 equal to beta v equal to 0, and the third null hypothesis is going to be based on the treatments. So, this is indicated by h naught t, which is tau 1 equal to tau 2 equal to tau v is equal to 0, right. Now, once you have got the linear model, you have got the hypothesis, you have got the constraints. So, you can use here either the principle of least square or the likelihood ratio test, and you can finally obtain the test statistics for these three null hypotheses. So, we are going to follow here the principle of least square, and using the same approach that you have used in the case of CRD RBD, we are going to follow here the similar steps, but definitely you will have to do this algebra afresh. Now, but since you know that how to do this algebra, how to differentiate and how to obtain the normal equation, how to solve them under this constraint. So, I am not going to give you here the all details, but I believe that now you are confident, you know how to get this algebra, and I would not like to spend time on this thing. So, that is now a very simple thing for you to find these expression. So, but briefly I can give you the step. So, we try to minimize the sum of squares due to random errors, which is now here the triple summation, that is summation over I, summation over j and summation over k, and all the summations are going from 1 to v, and the summation is over epsilon square I j k. So, now if you try to write down this sum of square s and you try to partially differentiate this s with respect to mu, alpha I, beta j and tau k, this will give you the normal equation. Substitute those normal equation to 0, try to solve them, and once you try to solve them, you will get here the estimate of mu here as a y bar triple naught, estimate of alpha I here as a y bar I naught naught minus y bar triple naught, the estimate of beta as a beta hat j, which is y bar naught j naught minus y bar triple naught, and estimate of tau as tau k hat y bar double naught k minus y bar triple naught. So, you can see here that these expressions are very easily obtainable if you have understood the one-way and two-way analysis of variance, right. The way you had written y bar I naught or y naught j in the case of two-way analysis of variance, you can write down here very easily y bar I double naught and y bar say naught j naught, right. And similarly, you can write down here from y bar double naught to y bar triple naught. For example, this is simply going to be 1 upon here n triple summation y I j k, and where your n is going to be here what? The total number of observation which are equal to here v square, right. So, now based on that now you can partition the total sum of squares into 3 mutually orthogonal sum of squares which are due to row, column and treatment, and one more sum of square that will remain as earlier, that SSE, that is sum of square due to error. So, if you try to see in the case of one-way analysis of variance, you had partitioned the total sum of squares into sum of square due to treatment and SSE. In two-way analysis of variance, you partition the total sum of squares into sum of square due to block plus effect plus SSE. Now, similarly, you are trying to partition the TSS in the case of three-way classification into sum of square due to row, sum of square due to column, sum of square due to treatment and SSE. And they are going to have a similar concept, they are going to be handled in the same way, that all these 4 components, they are in the form of quadratic form, they are mutually orthogonal to each other, right. And here I am writing here the terms what you are finally going to obtain. They have to be obtained exactly on the same way as you did earlier. The total sum of square is going to be obtained by triple summation I j k y I j k minus y bar triple naught whole square, and this can be expanded to triple summation y square I j k minus g square upon v square, right. If you remember, you had a correction factor which was earlier here as a g square by n. So, now and here is v square, and similarly you can write down here the SSR, which is the sum of square due to rows, which is here v into summation over I y bar I double naught minus y bar triple naught whole square, which is here summation over I r I square upon v minus correction factor, which is g square upon v square, where r I is the this double summation over j and k y I j k. So, as you had obtained the treatment total, block total in the case of two-way classification, here you are going to obtain here similarly like r I, t j and t k. So, similarly you can obtain here the sum of square due to columns here. So, what you have to do here? You have to just write a similar expression, that is SSC, which is equal to here V into summation over j y bar naught j naught minus y bar triple naught whole square, and if you try to simplify it, this will come out to be here summation over j c j square upon v minus the g square upon v square, which is the correction factor, where your c j is given by this double summation y I j k and summation over I and k. And similarly, you can obtain here the sum of square due to treatments, which is equal to here V into summation over k y bar double naught k minus y bar triple naught whole square, and if you try to simplify it, this will come out to be summation over k k square divided by v minus g square upon v square, and this the treatment total here is given by this quantity t k, which is double summation over I j y I j k. Right. So, if you try to see when you are trying to write down here the expression for this r I c j t k, they are very similar. If you try to obtain here, you can see here for example that it is here j and here I and k, and similarly if you try to take here it is k. Now, the remaining two subscript they will come over here in the summation I and j. So, if you try to just observe the way these things are going to be obtained, it is not very difficult to obtain these expressions directly. So, that depends on your practice and how are you going to observe this phenomena. Right. And similarly, if you try to obtain the degrees of freedom carried by the sum of square due to rows, column and treatment, so they are going to be exactly v minus 1 in each of the case. Right. And the degrees of freedom carried by the total sum of square will be n minus 1, which is here v square minus 1, and if you try to obtain the degrees of freedom of SSC by subtraction, which is v square minus 1 minus the degrees of freedom of rows, column and treatment, you will get here v minus 1 into v minus 2. Right. Now, you have obtained this sum of square, and similarly you can do the entire analysis under H naught row, H naught column and H naught treatment, and you can obtain the sum of squares due to error, and based on that you can obtain here all the expression about these various SSCs and various sum of squares. Now, if you try to see, if I try to do the same thing here, repeat the same thing, you will get completely actually bored, because these are very simple things. Yes, they are going to be little bit longer, lengthy, but as I say lengthy, that does not mean difficult or complicated, right. And as you already have done all this analysis of variance earlier, so you understand that how the terms are going to looking like and how they are obtained. So, now if I try to see the statistic for that test of hypothesis for H or R is going to be here f r, which is the ratio of mean square due to rows divided by mean square due to error. That will follow a f distribution with v minus 1 and v minus 1 into v minus 2 degrees of freedoms, and this is going to be a central f distribution under H naught. And similarly, under H naught C, you have to take the ratio of mean square due to column and mean square due to error, and in case of treatment you have a f statistics indicated by here f t, which is the ratio of mean square due to treatment and mean square due to error. And each of these statistics that is going to follow a central f distribution with degrees of freedom v minus 1 and v minus 1 into v minus 2. And based on that, now you can write the decision rule very easily, that you have to reject H naught R or say H naught C or say H naught T at alpha level of significance if the calculated value of f, which is here f r, f c or f t, is greater than the corresponding tabulated value at alpha level of significance with and with e minus 1 and v minus 1 into v minus 2 degrees of freedom, like as here and here. So, that is now very simple thing for you to do, that is not a very difficult thing. And obviously, if the null hypothesis is not getting accepted, then you have to use the multiple comparison test, no issues. And if you try to compile all this conclusion that you have obtained in the form of the analysis of variance table, then you have here 3 sources of variation: rows, columns and treatments, and then they are having the degrees of freedom with each E minus 1 with the corresponding sum of squares here as SSR, SSC and SSTR, and based on that you try to obtain the mean square due to rows, mean square due to column and mean square due to treatment, and then you have here the total sum of squares which is carrying V square minus 1 degrees of freedom, and the corresponding sum of square is indicated by TSS. And can you try to find out here the sum of square due to error by subtraction, and this SSC is going to carry V minus 1 into V minus 2 degrees of freedom. Now using these MSR, MSC, MSTR and SSC, you can obtain here the 3 statistics of F, that is FR, FC and FT, and based on that you can take a conclusion. And if you try to take here the expectation of say mean square due to rows, columns, treatment and this MSC, you have here a similar expression that the expected value MSR is going to be sigma square plus V upon E minus 1 summation alpha I square, and expected value MSC will remain as the same except that this term will become summation over j beta j square, and similarly for this expected value of MS treatment, this expression remains the similar, only the expression of summation over k cow k square is getting changed. And for the case of MSC, this will come out to be sigma square. So this is indicating that mean square due to error is providing us an unbiased estimator of sigma square, and this thing you can observe from here also, that if your H naught alpha 1 equal to alpha 2 equal to alpha V is accepted, that is 0, then this entire term becomes 0, and this is dependent only on the say sigma square, that is the error variance, and the similar conclusions can be drawn from the MSC and MSTR also. So now this completes the analysis of Latin square design, and you can see here that it was not very difficult, but the condition is if you have understood the one way and two way analysis of variance, then you can obtain the analysis of variance in the case of LSD without any problem. Right. Now I try to come on this here another aspect of missing plot techniques. So as I discussed in the beginning also, that it may happen in conducting a real life experiment that some observations are missed, and this may happen due to several reasons. For example, in a clinical trial, suppose the readings of blood pressure are to be recorded after 3 days of giving the medicine to the patients, and suppose the medicine is given to 20 patients and one of the patient does not turn up for giving the readings. So similarly, in case you are trying to consider an agricultural experiment, suppose the seeds are shown in the plots and their yields are to be recorded say after a couple of months, and suppose some cattle destroys the crop of any plot and the crop of other plot is destroyed due to storm, insect, etc. So now what will happen, that one or more than one observations are getting missed from the data that you were expecting to collect. So in such a situation, one option is that you simply ignore the entire experiment and conduct it again, but definitely that is not a very viable option, because that will result in the loss in the cost, time, labor, etc. So another option in such cases is that somehow try to estimate the missing value on the basis of available data. Right. Suppose you want to collect the observation on say 30 plots, but now you have a data on say 29 plots or say 28 plots, etc. And now using the available data, try to estimate the missing value, and then the estimated missing value is replaced back in the data, and now the data will look like as if there were no missing values in the data set. Now we can conduct the statistical analysis on the basis of this completed data set, and we are simply going to assume that the data is looking like as if all the data were available, but definitely we are going to estimate one value. So that is going to change the variability in the system and something about the statistical properties of the estimator, etc. So we need to understand those changes so that we can make the necessary changes in the statistical tools which we are going to apply. Right. And as I told you earlier that such an area comes under the array of missing data models, and a lot of developments has taken place. But in this lecture we are going to discuss the classical missing plot technique which was proposed by Yates, and this technique has got a following steps. The first step is estimate the missing observation by the values which make the error sum of a square to be minimum. This means what? When you want to estimate a missing value on that data, you have to first describe what is your criteria, whether you want to, what you really want to achieve. For example, suppose if I say you want to obtain the value of missing data such that the sum of a square due to error is maximum or say minimum, but definitely we would always like SSE to be as small as possible. So, in this technique we assume that we would like to estimate the value of x such that the SSE is minimum. Now, once we have obtained the value of the missing data, then we try to substitute the unknown values by those estimated values, and then we try to express the error sum of a square as a function of these unknown values, right. Then minimize the error sum of a square using the principle of maxima minima, or you can use any other principle, but in the case of principle of maxima minima we try to differentiate the SSE with respect to the missing value, put it equal to 0, get the normal equation, and then form a linear equation, and then you try to solve those normal equation and then try to form such linear equations. Now, the question here is that how many linear equations are you going to frame? So, it is as simple as that. If there are two missing values, then you are going to differentiate the SSE with respect to both the missing values. So, you are going to get here two linear equation, and if there are three missing values, then you are going to differentiate the SSE 3 times with respect to each of the missing values. So, you are going to get here the 3 linear equation, and if there is only one missing value, then you are simply going to differentiate SSE only once, and then you will get here a single linear equation which you can solve, right. So, it is as simple as that. Try to differentiate SSE as many as number of the time the values are missing, right. So, form as much a linear equation as the number of unknown values, and then we try to solve those linear equations simultaneously, and whatever are the solutions, they will provide us the value of the missing data. Then once we have obtained the value of the missing data, then we try to impute the missing values with the estimated values and complete the data set. So, now the data set will look like as if no value was missing in that sample. Now, after this you just apply analysis of variance tool. For example, in this case we are talking of analysis of variance tool, but you can apply the required statistical tool whatever you are trying to do. And after that we have to make a certain adjustment that we will try to discuss. So, one adjustment is that the error sum of squares thus obtained is corrected, but the treatment sum of square is not corrected. That is what you have to keep in mind, because once you are trying to assume that some values are unknown because they are missing. So, that is going to affect the degrees of freedom, and that is also going to affect the sum of squares. So, this adjustment is made only on the error sum of squares, right, and the number of degrees of freedom associated with the total sum of square is subtracted by the number of missing values, and then the adjustment is made in the error sum of square, right, and there is going to be no change in the degree of freedom of sum of square due to treatment, right. So, this degrees of freedom are going to be adjusted between the total sum of squares and the error sum of squares. How this I will try to show you here. So, now let me try to take here couple of examples. So, suppose we try to consider here the setup of randomized block design, and we assume that there is only one value which is missing. Well, before I try to show you the analysis, my request is that you try to please pick up the approach and philosophy behind this missing plot technique, that how I am going to obtain the expressions. After that the algebra is very simple. So, suppose one value is missing, and we assume that the value in the ijth cell is missing. So, you can recall this two-way layout is the same layout that we had considered when we discussed about the randomized block design, So, now you can see here I am writing here yij is equal to x, which is here the missing value. And you can recall that in the case of randomized block design, we had obtained the block total, treatment totals, etc. So, now you can see how those block totals and treatment totals are going to change. Now, all the observation in the first row are available. So, that is going to remain as earlier. Block total will be indicated by B1, and similarly the block total B2 will also remain the same. Now, there is one value here x which is missing. So, the corresponding ith block total is now going to be expressed as say y prime I naught plus x. So, now y prime I naught is the sum of all the observations which are available to us and plus here x, right. So, this is indicated here. And similarly, if you try to see here all B1, B2, B here, they are going to remain the same, only the BI is going to change, and the same process is going to happen when you are trying to consider the treatment total. You can see here this column will remain the same, this column will remain the same. So, their corresponding treatment total T1 and T2 will also remain the same, only the J treatment total Tj is going to be expressed by y prime naught j plus here x, where y prime naught j is the sum of all the observations which are available to us and plus here x, and all other out of T1, T2, Tv they will remain the same except the G treatment total. And similarly, the grand total G will be also be the sum of all the observations that are available, which is indicated by y prime double naught and plus here x, right. So, now this is pretty simple layout. Now, if you try to see, you try to recall the expressions of TSS, SS block, SS treatment, SSE in the case of randomized block design, and try to rewrite the sum of squares as a function of x, which is the missing value. And here you have to just use your very simple elementary knowledge about mathematics to do it. So, now in this case you can see here that the correction factor that was written earlier as say g square upon n. So, now g is becoming here y prime 00 plus x. So, the correction factor will become y prime 00 x plus whole square and divided by b into v, right. So, similarly, you had obtained the TSS. TSS was obtained earlier as a double summation y square I j minus the correction factor. So, this will become here the x square plus all the terms which are constant with respect to x, they are some numerical values minus the correction factor, right. So, here I am more concerned in dividing the terms into two parts which are a function of x and which are not the function of x. And similarly, if you try to see the sum of square due to block can be written by here y prime I naught plus x whole square. This is the term which is containing x plus all other block totals in which there is no x. So, that is going to be constant when we are trying to differentiate it with respect to x minus the correction factor. And similarly, the sum of square due to treatment will become here 1 upon b y prime naught j plus x whole square plus here all the terms which are constant with respect to x minus the correction factor, and then SSE is simply going to be TSS minus SS block minus SS treatment, which is just obtained here, right. So, this is what you have obtained. Now, what we have to do? We have to simply find out here the value of x such that SSE is minimum. So, for that I can just partially differentiate SSE with respect to x, put it equal to 0. I will get here this equation, and you simply have to solve this equation. And do you expect that I should show you that how to solve this equation? Certainly not. So, if you try to solve it here, this value will come out to be here like this x. So, now means everything in this term is known to you. So, you can substitute the value of x, you can substitute it in the data, and then you can conduct your analysis of variance. Well, in this case also you need to verify the second order derivative condition for x to provide the minimum SSE, and that is very easy, that if you try to do it, that will assure that this chosen value of x is going to minimize the sum of squares due to error, right. Now, suppose if I try to extend this case, that suppose we have here two missing values, then suppose the missing value here are x and y. Now, you see, try to move forward only if you have understood the earlier case, because in this case I will simply try to give you the basic steps, but you need to do this algebra yourself, right. So, now you can see here that in the earlier steps I have simply written the sum of square due to block, total, SSE and TSS, and then I have written the SSE and I have differentiated it. So, the same steps I am going to follow here also. So, first we try to write down here the row sums, or we call it as the block totals, say here R1x plus R2y. So, once again R1 is the sum of all those observations which are available, and R2 is also the sum of those observations which are available in that row, right, and plus here those missing values x and y. And similarly, you can obtain the column sums here, C1 plus x plus and C2 plus y, where C1 plus x is the sum of all those values which are known to us, indicated by x, and then the value which is unknown to us, which is here x. And similarly, in the column in which y is appearing, there the column sum is going to be C2 plus y, where C2 is the sum of all those values which are available and y is the value which is missing, right. And then we try to write down here the SSE. So, SSE will come out to be x square plus y square minus sum of square due to row minus sum of square due to column. And then SSE can be obtained here as by TSS minus SS block minus SS treatment, and then you can see here this term will come out to be here like this, and you can see here x and y are appearing here, right. That is pretty simple expression, that is only a couple of minutes job, and I expect that you should be able to do it. Now, we try to differentiate this SSE partially with respect to x and y. We get here these two equations like this one here. You can simply differentiate it and obtain it, and then you simply try to solve it. So, here we have here two this equation, you can simply solve them, you can obtain here the value of x and say here the value of y, and then you can just substitute them back, and then you can conduct the entire analysis, right. So, this is how we are going to conduct the analysis after getting the values of x and y. Right. So, now what adjustments you have to do in this analysis of variance? So, first we have to obtain the within block sum of squares from the incomplete data, and then you have to subtract the correct error sum of square from this one, and this will give us the correct treatment sum of squares. And then you have to reduce the degrees of freedom of error sum of squares by the number of missing observations, and no adjustment another sums of square is required, right. So, these are the adjustment that you have to make here. Now, similarly, if you try to do the same exercise in the case of Latin square design, that is pretty simple. But again, I will request you that if you have not understood this analysis, what I have just presented in the case of randomized block design, then you try to take a hold, and then after you have understood, then you try to proceed further. So, in the case of Latin square design, suppose x is the value which is missing in the ij kth cell, right. So, now you have to do the same thing, you have to just obtain the sums in row, column and treatment of those values which are known to us, right. So, R is going to be the total of known observations in the ith row, C is going to be the total of known observation in the jth column, and T is going to be the total of known observation receiving the care treatment, and S is the total of known observation, right, sum. Then now you can simply define here the correction factor here, say S plus x whole square upon the number of observation here V square. TSS is going to be simply x square plus terms which are constant with respect to x minus correction factor. So, similarly, you are going to get here the sum of square due to rows, column and treatment. They are again going to be on a similar nature, that the row sum here becomes here R plus x whole square, R is the known sum and x is the unknown sum. And similarly, in the case of column, that C is the known sum, x is the unknown value, and then the case of sum of square due to treatment, T is the known value and x is an unknown value. So, now you can obtain here these three terms and plus all the terms which are constant with respect to x, that means there are some numerical values, they will be there in all the three terms minus the correction factor, right. This is the same thing which we have done in the case of randomized block design. And then now based on this expression you can find out here SSE, which is here TSS minus SSR minus SSC minus SS treatment, which will come out to be here an expression like this one. Right. Now you simply have to just differentiate it using the principle of maxima and minima. Try to differentiate it, put it equal to 0, you will get here such an equation. Just try to solve it here, and then you will get here this value here x, which is missing. Now this value is available to you on the basis of the data set what is known to us, and based on that now you can conduct the analysis of variance. So in this case also you have to do all the steps that you did in the case of randomized block design, and to get the correct treatment sum of squares you have to just follow the following steps. So first ignore the treatment classification and consider only rows and column classification. Then value that you have obtained in the place of missing observation, then try to obtain the error sum of squares from the complete data, say let us call it say here SSE1, and then try to obtain the error sum of squared based on the Latin squared design that was obtained earlier, and suppose this is indicated by here SSE2, and then the corrected treatment sum of square is obtained by SSE2 minus SSE1. And then about the degrees of freedom, try to reduce the degrees of freedom of error sum of square by the number of missing values. And then now you have here all the things, and now you can conduct your analysis of variance, right. You simply have to adjust the degrees of freedom, and you have to obtain the corrected treatment sum of square, and now you have here all the ingredients which are required for the analysis of variance table. So now we come to an end to this lecture, and you can see here this was not a very difficult lecture. There were two topics which are very simple and straightforward, provided you have understood the earlier part. And I am sure that if you have understood the earlier part, there should not be any problem in understanding this lecture, but definitely just by watching the video is not going to help you. You have to do this analysis with your own hand, using your own pen, own paper, and this will give you the confidence, because the algebra is simple, straightforward, there are no complications, and the only thing is what you have to understand that how these expressions are going to be obtained. So in this lecture I have a very strong recommendation for you and a very simple request also, that whatever I have done right from the beginning, try to do it yourself and try to understand that why are you trying to obtain any step, and if you get stuck, then you try to look into the slides and try to obtain the results, and this way you will get lots of confidence. So now with this lecture I will complete this three popular designs, CRD, RBD and LSD, and now from the next lecture I will try to take up the chapter on incomplete block design. So now you try to revise it, practice it, and I will see you in the next lecture. Till then, goodbye.